Hello everyone, this is the second lecture in the fourth week. So, in the previous lecture we derived the relation between the error function at x k plus 1 and the error function at x k, right. So, the error function at x k plus 1 is less than or equal to lambda n minus lambda 1 the whole squared plus lambda n plus lambda 1 the whole squared into the error function at x k, right. So, when lambda 1 by lambda n is very low, the number of iterations that it takes to complete to converge to the solution is really long, and we also looked at the illustration, right. So, let me restart with the illustration at, in this lecture. Okay. So, consider so if you recall f, when f was x 1 squared plus x 2 squared, right. So, that implies that h is 2002 and lambda 1 by lambda 2 is just 1, because lambda 1 is 2, lambda 2 is also 2, right, and it took, I mean the convergence took just one step, occurred in just one step. Okay. So, when the function became 2x1 squared plus x2 squared, right. So, h is 4002, now lambda 1 by lambda 2 is half. So, convergence took 5 steps in this case. Now, when it was 5x1 squared plus x2 squared, h is 10002, lambda 1 by lambda 2 is 1 by 5, and here the convergence took 8 steps. And when it was 50x1 squared plus x2 squared, h was 100,002 and lambda 1 by lambda 2 is 1 by 50, and this took 316 steps. And finally, when f was 100 x 1 squared plus x 2 squared, h is 200,002, lambda 1 by lambda 2 is 1 by 100, and this took 973 steps. So, all of this we looked at in the Python code in the last class. At the end you saw this particular curve. So, where it took 973 steps, and the the trajectory is just baffling. I mean, it started at 1 comma 100 and it keeps oscillating for so long, for 973 steps before converging to 0 comma 0 here. Okay. So, and what is the reason? It is because of this quantity that we had written down, e of x k plus 1 is, I mean, it depends on lambda n and lambda 1. So, if it turns out that lambda 1 by lambda n is very low, then the number of steps it takes is just quite huge. Okay. All right. And yeah, so this actually gives you a picture about how the gradient descent algorithm works, right. And I mean, what all we have analyzed is only for a quadratic function, right. What happens in case if the function is not quadratic, right? You can use the algorithm safely, no problem. So, just that the H matrix keeps changing for every iteration, right. So, the Hessian is not the same if the function is not quadratic, right. So, and we may also have to use backtracking line search instead of the exact line search algorithm that we were using for this quadratic function. Okay. So, we will see some examples before we move to a more sophisticated algorithm than the gradient descent algorithm. Okay. So, let us consider an example which I mean it is hard to do analytically. Okay. So, let f of x1 x2 be x1 squared e power x1 plus e power x2 plus x2 squared e power x1. Okay. So, if you are sharp enough you would have immediately found that the minimum occurs at 0 comma 0 because yeah, both of these terms are positive, in fact non negative, and they become 0 only when x1 equal to x2 equal to 0, right. So, the minimizer clearly is 0 comma 0, but let us see how we can derive the answer for this particular function. Okay. So, let us actually fix x0 to be 1 comma 1. Okay. So, yeah, I do not think there is anything else to be initialized. Okay. Yeah. So, if you we are just going to implement this algorithm now. So, we have initialized x0, tolerance is as usual we are initializing it to 10 power minus 6. Okay. And we will first choose dk equal to minus gk. We should choose alpha k only by backtracking line search algorithm because exact line search algorithm is not going to work with I mean analytically intractable problems, and we write xk plus 1 equal to xk plus alpha dk or minus alpha k gk and k equal to k plus 1. So, we will implement this particular algorithm. Okay. So, we just have to make some changes to the algorithm that we have with exact line search. Okay. So, yeah. So, I will write it as a separate algorithm. So, I am just copying the algorithm in the first place just to I mean because I mean the structure is more or less the same except for the exact line search algorithm, right. So, f of x is, if you recall, x1 squared into e power x1 x2 plus x2 squared into e power x1, sorry, yeah. And now you have to find the gradient. So, yeah, let us find it. So, x naught squared is so since you have x naught squared e power x1, right. So, that is 2 x naught into e power x1, 2 x naught into e power x1 plus so this is just e power x naught. So, it is x1 squared into e power sorry x1 squared into e power x naught. Okay. 2 into x1 into e power x of 0. So, I mean it is going to be similar plus x naught squared into e power x1. Yeah, fine. So, I mean if this is not very clear you can understand it this way. So, yeah, when you differentiate it with respect to x of 0, right. So, you get 2 x naught e power x1 plus x1 squared e power x naught. You differentiate this with respect to x1, you get 2 x1 e power x naught plus x naught squared e power x1. Okay. All right. So, we will start with 1 comma 1 as we just mentioned, and h is not required since we are going to use backtracking line search. So, fine, yeah, these are going to remain the same, and okay. So, the value of alpha needs to change. How should it change? So, I will just start with 1 and we will use the backtracking line search algorithm straight away. So, it is f minus alpha into g because f of x plus alpha d is just x minus alpha into grad of x. Okay. So, minus f of x greater than c 1 into alpha into grad of x dot minus grad of x. So, I will write a minus in front. So, when this is true, you just have to multiply this by a factor of rho. So, I need to initialize rho and C 1. So, let me do so here, rho and alpha. So, that is 0.8 and 0.75. I am using the same values what we had used in the illustration. Okay. So, this part is backtracking line search. So, note that this part is the defining the function, this part is defining the gradient, this is defining x 0. Okay. This I am initializing everything, k equal to 0, rho equal to 0.8, alpha equal to 0.75, y 1 y 2 for the plotting purpose. Okay. And yeah, so while norm g k greater than the tolerance which is 1 e minus 6. So, yeah, I am printing them. So, this part alpha equal to 1 while and alpha equal to alpha into rho. So, this is another method of writing alpha equal to alpha into rho. Okay. Alpha equal to alpha into rho. I mean, so both the commands are the same. So, this or this, they are the same. Okay. And x is equal to x plus alpha d. So, d is minus g. So, yeah, you have x minus alpha into g, and yeah, so I am just appending the values of y 1 now. Yeah, and I am adding k. So, here also I can write it as k plus equal to 1. So, this is the same as writing k equal to k plus 1. Okay. Fine. So, let us check how this algorithm works. C1 is not defined. Oh my god, this is C1. Okay, sorry. Great. So, it has converged in 30 steps and yeah, no zigzags, almost it goes by a nice straight line. Okay. No issues. So, yeah, this is all is the code to find the minimum of x 1 squared e power x 2 plus x 2 squared e power x 1. So, note that you can use this exact same algorithm for any function, right. What should you change? You have to change f of x, grad of x, okay. Sorry, yeah, f of x and grad of x of course has to be changed, and if you want to change the initial point you can do so. And I mean, yeah, for some problems you may also have to change the values of rho C 1 and the initial value of alpha as well. Okay. So, that comes because of the backtracking line search initializations. Okay. So, otherwise, yeah, I mean, you can put any function in the same algorithm. I mean, you can copy down this algorithm for example, and just change f of x, grad of x, and if required the initial point, okay, and the algorithm is actually going to give you the answer. Okay. So, you can try for certain functions, okay, yourself. So, as an exercise, try for the following functions. So, say f of x 1 x 2 is okay, and so so this is 1, okay, in case you did not understand. Yeah. So, this function is actually called as the Rosenbrock function. Okay. So, the convergence in this function for any algorithm will be very slow. Okay. So, and you can see that the answer clearly is 1 comma 1, there is a unique minimizer and it is at 1 comma 1. Okay. So, choose some other point, let us say 0 comma 0 or half comma half or something like that. Okay. And yeah, so such a function is actually called as the Rosenbrock's function. Okay. And you can also check for this function x1 e power x2 plus x2 e power x1. Okay. So, not much of a change, you just have instead of x1 squared and x2 squared you have x1 and x2, but you can see that this is not a problem for which you know the answer straight away for, right. So, yeah, you can find the answer by applying gradient descent algorithm, I mean using the Python code that we have just constructed. Okay. Fine. So, I will close the discussion on gradient descent at this point. Okay. And so, we have found quite a bit of issues with gradient descent, right. So, and one thing is, if you have a quadratic function where lambda 1 by lambda n is much less than 1. Okay. So, gradient descent is going to take forever to come to the answer, to converge to the answer, right. So, and it could be the functions could be as simple as 100 into x1 squared plus x2 squared, right. So, I mean any student who does high school math would tell you that the answer is 0 comma 0. So, it is such a simple function, but yeah, the gradient descent algorithm takes forever to compute an answer to this algorithm, right. So, how can we make this better, right. So, is there a better way to get to the answer, right. So, we will now discuss a particular method. Okay. So, instead of using dk equal to minus gk, that is the negative of the gradient of f at xk, right, we are just going to use the coordinates. Okay. So, let us see how we do it. Okay. So, let us actually consider a simple function. Okay. So, let f of x1 x2 is half x transpose hx, where h is equal to lambda 1 lambda 2 dot 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 lambda n, where with lambda I positive for all I. So, all lambda 1 to lambda n is positive, and yeah. So, f of x1 sorry, yeah, this is x1 to xn, sorry about that, f of x1 to xn is half x transpose hx. So, if you expand, nothing great, you will just get lambda 1 by 2 x1 squared plus lambda 2 by 2 x2 squared plus dot 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 plus lambda n by 2 xn squared. Okay. Note that lambda 1 and lambda n can be anything, it need not be the same. Okay. So, that means lambda 1 by lambda n is could be very low, I mean no issues with that, that is basically what I am saying. Okay. So, I am just going to do a very small change when you compare it with the steepest descent or the gradient descent algorithm. What is it? Instead of dk equal to minus gk, okay, I am going to choose d1 equal to minus 1 0 0 0, d2 equals 0 minus 1 0 0 0 0 and so on, dn is 0 0 dot 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 minus 1. Okay. Basically the negatives of the coordinates. Okay. So, d1 is just like I mean the other axis remains the same, but in the x1 axis I am going to move in the negative direction. d2 is the other axis remains the same, in the x2 axis I am going to move in the negative direction, and dot 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 dn is going to I mean I am going to retain all the other coordinates, and the xnth coordinate I am going to move in the negative direction. Okay. So, that is all I am going to do. So, let us check what happens in this case. Okay. And yeah, let x naught be any x1 0, x2 0, dot 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 xn 0, could be any value, does not matter. Okay. And I mean I do not think I need to tell you that the answer is at 0 0 0 0 0, right. Okay. So, let us just blindly apply this algorithm, but just I mean I am just going to change, instead of dk equal to minus gk I have chosen certain dk's now. Okay. So, let us see what happens. So, you have x1 equal to x naught plus alpha naught d naught, right, and if you recall alpha naught, right. So, yeah, x naught is first x1 to xn 0, and what is alpha naught? Alpha naught is gk transpose. So, yeah, okay. So, maybe I should have written that in the first place. So, yeah, if this is f, what is del f? So, del f of x is lambda 1 x 1, lambda 2 x 2 dot 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 lambda n x n. Okay. So, I should have written that in the first place. So, yeah, this if you recall it is minus, so it is G 0 transpose actually. So, G 0 transpose d 0 by d 0 transpose h d 0 into d 0, and d 0 is something that we know, it is minus 1 0 dot 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 0. Okay. So, x 2 0 to x n 0 is going to remain the same. So, we will just calculate what is this quantity. So, G 0 transpose, if you recall, is yeah, lambda 1 x 1, lambda 2 x 2 dot 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 lambda n x n. Okay. Now, what is d 0 transpose h d 0? You can see that it is just lambda 1, right. So, h is given here, right. So, you just multiply d 1 transpose and d 1 here, you will just get lambda 1, right. So, the denominator is lambda 1 and the numerator is lambda I mean minus lambda 1, right. So, when you have a yeah, so you have a minus and a minus here, so it is a minus. So, the first quantity is, so so note that G 0 transpose d 0 is lambda 1 x 1 0, sorry, yeah. So, I should have written zeros here, and d 0 transpose h d 0 is lambda 1. Okay. So, yeah, so this is minus lambda 1 x 1. Yeah. So, when you substitute this here, you get 0 in the first coordinate, and the remaining coordinates are x 2 0, x 3 0 dot 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 x n 0. Okay. So, what is x 1? It is very simple. I nullify the first coordinate and the other n coordinates are remaining the same. Okay. Fine. Now, let us compute x 2. X 2 is x 1 plus alpha 1 d 1, and yeah. So, this is okay, 0 x 2 0 to x n 0. Now, what is G 1 transpose d 1 by d 1 transpose h d 1, and this is 0 minus 1 to 0. Okay. So, again G 1 is just lambda 1 x 1 1, lambda 2 x 2 1 and so on. I do not need to write that, I will write this in the sides. So, G 1 transpose d 1 is just minus lambda 2 x 1 x 2 1, and d 1 transpose h d 1 is just lambda 2. right. So, this quantity is minus x21 and so sorry, I am sorry, this is x20, x21 does not matter, but fine. So, the second quantity is now nullified. So, you get 0 0 x30 dot 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 xn0. Okay. So, what has happened at the end of second step? The first element of this vector is nullified to 0 and the second element has also been nullified to 0. Going as such, you can derive that at the nth step you will have all zeros. Okay. Verifying this is not a big issue. So, what have I done? I have considered quadratic function of a particular form, right. So, where the Hessian matrix is a diagonal matrix, okay. Lambda 1, lambda 2 dot 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 lambda n can be anything. I mean no constraint like lambda 1 by lambda n has to be close to 1 or equal to 1 or nothing, it can be anything, okay. Lambda it is just constrained to be positive, okay. And I have given you an algorithm where in n steps I got the answer, is not it. So, this algorithm is actually called as the coordinate descent algorithm. Okay. So, for example, if I had given the coordinate descent algorithm the function 100 x1 squared plus x2 squared to minimize, okay. So, it would have done in 2 steps because n is equal to 2, is not it. Our poor steepest descent algorithm actually took 973 steps, right, but coordinate descent algorithm would have finished it in 2 steps, right. So, but we should check if this works for other functions as well, at least other quadratic functions, if not for I mean other sophisticated functions. Okay. So, let us consider an example, okay. An example where f of x1 x1 to xn is half x transpose hx, but h is not diagonal, okay. H is positive definite also, but it is not diagonal, okay. So, let us consider a simple example and see if I mean how this wonderful coordinate descent algorithm works, okay. So, let f of x1 x2 equal let us say x1 squared plus x1 x2 plus x2 squared, okay. So, this is in simple words it is half x transpose hx where h is 2 1 1 2, okay. So, it is not diagonal as you can see, but it is positive definite. So, let us blindly apply coordinate descent algorithm to see if we get the answer in 2 steps, as I mean it was the case with a case when H is a diagonal matrix, right. So, let us pick, let us say x naught equal to 1 comma 1. So, let x naught equal 1 comma 1, okay. So, x1 is x naught plus alpha naught d naught. So, you have 1 comma 1 minus, so the same thing g naught transpose d naught and all that, but d naught is minus 1 comma 0. So, but g naught is slightly different, it is hx. So, that is this 2 1 1 2 into 1 1 which is 3 3, okay. And so, if you multiply it with minus 1 0 it is minus 3 and d naught transpose h d naught is 2. So, you have minus 3 by 2 into minus 1 0. So, you have so yeah, this remains as 1, no issues, but here you have minus 1 by 2. Okay. Okay. So, x 1 is minus 1 by 2 comma 1, and let us see what happens to x 2, that is x 1 plus alpha 1 d 1. So, you have minus half 1 minus. So, yeah, now we will have g 1 is 2 1 1 2 minus 1 by 2 1, which is minus 1 plus 1 is 0, and minus half plus 2 is 3 by 2. Okay. So, yeah, and if you multiply with minus 1, you get minus 3 by 2 in the numerator, and this is going to be 2 again. So, this is minus 3 by 2 by 2, and this is 0 minus 1. So, this is not going to change because it is 0, it is going to be minus half again, but here you have minus 3 by 4, which is 1 by 4. So, it is very clear that yeah, this is not 0 0. So, what this tells us is, yeah, coordinate descent algorithm works specifically when f is half x transpose h x, when h is a diagonal matrix and a positive definite matrix, but even for other positive definite matrices it does not work. Okay. So, yeah, we will see how to rectify the issues in a non diagonal matrix in the next class. Thank you.